some, it will shift to the other side to keep it balanced. If you remove some, then you're going to have to fill in what you just removed to go back to being balanced. You guys with me on that? So let's write an example. If the concentration of, let's say, NH3 is increased, in which direction will the equilibrium shift? If the concentration of NH3 is increased, in which direction will it shift? I really urge you to use the seesaw analogy, use your arm, use your finger, use your pen, pencil, so you always start balanced, always balanced. If we take and add more, if we take some NH3 and add more NH3 to this side, it's going to be all screwed up. How does it shift to fix that? That's, when I say shift, that's what I mean. So the NH3 is added, so it's going to be disrupted. That's the stress. How does it shift to go back to being balanced? Raise your hand. Which way are we shifting? Leah? Which way? Oh, you're trying to figure it out. Here, I'll use this. We're balanced originally. If I add more NH3, which side of this is going to, imagine it's a seesaw, which side is going to go down? I can do it from your side, okay, from your perspective. So is the right side or the left side? Where's NH3?
On the right side.
So if I add more, this will go down. Like a seesaw. You put more people on this side, it goes down. Does that make sense? Everybody with me? That's not the shift. It hasn't shifted yet. That's the stress. How does it shift? Some of the products have to move over here to make more reactants to go back to being balanced. So the answer is we shift left or towards the reactants. So we shift to the left or towards reactants. Now, as a result, let's make sure we understand this. If we are shifting to the left, we are making more N2 and H2. That should make sense to you. After, we've been taking chemistry here for a while now, talking about reactions. If we shift towards the reactants, you're making more of them. You have to make more because you need to balance it again. So again, I'm going to just repeat it. If I add more NH3, this side goes down. So eyes up here. Add NH3, this side goes down. I need more reactants. It needs to be heavier on this side. So these products actually make reactants because it's a reversible reaction. And as they move this way, it starts to balance out again. And then we're back to equilibrium. We're back to a 2-to-4 ratio when that happens. So if we're going this way, we're making more N2 and H2. Okay. Next question. If some NH3 is removed from the reaction, how will the equilibrium shift? How will the equilibrium shift? Again, the whole seesaw analogy is literally the only way to do this, I think. Now we're removing some of the ammonia. So it's a 4-to-2 ratio. What if we decrease the 2? What if we change that? Make it a smaller number. Then we don't have the ratio. It's all screwed up. It's not constant anymore. It's not balanced. Trevor, which way are we shifting? Are you confident?
Not really.
Okay. Did you do the seesaw on your head?
Yeah. We're taking it from the right side.
So, well, if we're removing NH3, there's none here and there's none here. Here's your NH3. So you have, the way we do all of these problems, you guys need to visualize that these reactants and products are like people sitting right on top of this seesaw. So if I have NH3 sitting right here and I just knock them off.
Yeah, it should flat.
So we're gonna go like this, okay? That's not the shift though. That's the stress. The shift is what happens after the stress. So initially we're here. Make sure if you understand, these couple examples going to make temperature and pressure easier. So everybody stay with me, and I'm talking to Trevor, but obviously everyone's paying attention. So I knock off some of the NH3. This is what happens. Hasn't shifted yet. Now, how do the reactants and products shift to try and go back to being balanced?
So they should be right.
Correct. So these two are going to react together and form more NH3. So this side gets heavier. Now we're back to being balanced. So we're shifting to the right. Shifting to the right. And as a result of that, if we're shifting this direction towards the products, the concentration of N2 and H2 are decreasing. This is a tough concept because I can't show you that. I can't show you particles, even if I do a demo. I have one I want to show you, but it's just a color change, and it's hard for you to really visualize. I get that, so I try to use this seesaw analogy to help. So again, if we take something off of this side, it gets lighter. That's not what we want. So some of the ones on the left here must come together, make products to go back to being balanced. Questions? Okay, next we're going to talk about temperature. Write this question down. If the temperature on this reaction is increased, if the temperature on this reaction is increased, in which direction will it shift? Which direction will the equilibrium shift? And we'll end with temperature. We're not going to get to the pressure today. And then your worksheet will practice just concentration and temperature. What we'll do tomorrow is go over the homework and then take the quiz. Or about half and half.
So we're going to have a quiz in class and then in a lab too?
Yep, double quiz tomorrow for people in period 8. But the one in lab is easy. Just make sure you know the parts of that potential energy diagram. So review those for the quiz tomorrow and Friday. All right, here's the only rule with temperature. When you see temperature, you need to find the heat. We treat the heat as if it's an actual substance sitting on this meter stick, yardstick, whatever. So 91.8 sitting right here. Okay, so I really need you to focus. We only got about 5 minutes, a little less. So pay attention. 91.8 sitting right here. Energy and temperature are related. Temperature measures the amount of energy, right? So if the temperature goes up, that's kind of like saying this number goes up. So if we treat the energy as if it's a substance sitting on this seesaw, and we add more heat to this side, what happens to this? Okay. How does it shift to go back to equilibrium? Some of your products must shift to make reactants to go back to being balanced. So the answer to this question is we shift left. So if we increase the temperature, we shift left towards the reactants. You shift left, and that's because when you increase the temperature, you're increasing the amount of heat. If you add heat to this reaction, you're adding heat to this side. It doesn't want anymore, it only wants 91.8. So it shifts some of that to this side to go back to being balanced. Hold on one second. And if we're shifting left, that means we're making more reactants, less products. So our concentration of N2 and H2 will go up. Our concentration of NH3 will go down. This whole, the star part that I keep adding is actually more Regents level. They will ask, okay, temperature is increased. What happens to the concentration of H2? So you have to think, all right, temperature's increased. This is what happens. We shift left. That means I'm making more of these, so it gets heavier. Oh, that means it increases. Yeah, it's a lot to figure out at once. That's why this analogy really helps, and we're going to practice. I have 2 worksheets that we're going to just do a whole bunch of practice problems. I got one more question, then we're done. Yeah.
Would it also, like, if you didn't think of the energy, could you think of that it would, because of the energy, it would be making more NH3, so you'd have to account for that instead of the other way?
If you increase the temperature on an exothermic reaction, it doesn't react as well, so it goes in the reverse direction. That's the best way I can say what's really happening. Because exothermic reactions give off heat. So if you put them in a hot environment, there's less chance of them releasing heat because energy goes from hot to cold. So if the environment is not cold enough, it doesn't release as much heat as it's supposed to, so it starts working the other direction. That's the real answer, but that's confusing. You don't need to know what I just said, but I'm trying to address your question. All right, here's the next one here. If temperature is decreasing, or if temperature is decreased, how will the equilibrium shift? If temperature decreased, if the temperature is decreased, how will the equilibrium shift? Here's your worksheet while you're figuring that out. Never look in the right drawer first. Don't put that away. Let me give you some advice there. Okay, so real quick, and if the bell rings, just give me another 10 seconds. Right here, this side right here. This side right here, look up here. You got 2 sides. You got the 2 charts and then the 1. This side, just do 1 through 8. Don't do the pressure questions. Don't do the pressure questions. On the other side, same thing. 1 through 8 on top here, 1 through 8 on top, and 1 through 6 on the bottom. Yep, 1 through 6. So don't do the pressure questions. That's due tomorrow. Look up here, real quick. Now, again, up here, stay with me. I know we're almost done. If I remove the heat, decrease temp, what happens to this side?
Goes up.
Goes up. It didn't shift yet. Now we're shifting right to go back to equilibrium. So we shift right. We shift right. If you're confused, that's okay. All these practice problems, you will get it by the time we're done going over it. I have AP review class today, but if you really want to stay and work on